Okay, everyone, so today's our last day of class, and I just want to make sure that you know what's left to do on Lon Kappa here. So here we are, and tonight the final exam conflict sign-up is due on Lon Kappa. Now, your final for the L1 people is right in this room, and for the online people, it's going to be in Altgeld. That's posted, and I'll post it here as well. But this room's going to be really crowded because not enough people signed up for the conflict. So what I'm going to do is, if anybody in L1, I guess I should open it up to the online people too. Anyone who wants to take the conflict, which is at 7 p.m. You can sign up for it. We'll take like the first 20 people who sign up, because we have about 20, too many people, especially for L1. So if you sign up, you might get preference if you're in L1, because we need to make sure that everybody has every other seat and has some space for the final, and right now we don't. So if you want to just do it, you don't have to have a reason anymore. You can just sign up and with no reason, and we'll choose some of you. First come, first serve. Does that sound okay? All right. So now the other thing that's due is the 2 bonus opportunities on Wednesday, and we're having office hours 4 to 6 every day until the final. All right, so you're probably all wondering about your grade. How hard do you need to study for the final? I gave you instructions, but if you go to grading, I don't know if you noticed, but there is this grade calculator here so that you can put in your exam 1 grade, your exam 2 grade. For example, let's say you got an 80 here, a 90 here, etc. 79, let's say, whatever. And whatever your homework percentage is after your 3 lowest scores are dropped. So I'll make sure Compass is up to date. I don't think it is right now. I don't think I'll make sure after class that the homework percentage will have your 3 homeworks dropped. And let's say after the 3 homeworks dropped, you got like a 98 or something. And now you have to estimate your bonus percentage, because that depends on the last 2 assignments that were there, whether you're in the online or the in-person class, how much your notebook's going to be worth, etc. But you can estimate that, if you're going to, or you could just do it either way. See if it's worth filling out your whole notebook, whatever you want to do. So estimate your homework percentage, and let's say you estimate it, and you estimate it to be 80%, including the notebook points. And what you want on the final, you put in here. So let's say, could you get an A, a 90? So you put in the lowest possible A minus, like that, and see if you can do it. And we'll calculate it. And yes, it tells you you need 94 on the final. So you say, well, maybe I won't turn in my notebook points or whatever. Don't cut it too close, and then just see what happens. And you calculate, and then it will change. Then you need a 96 on the final. I'm just doing this for you because I know you have a lot of classes, and you need to estimate how much time to spend on each one. So this is to help you do that. All right? So make use of that, and I'll get the homework, I'll get all your grades updated on Compass so that you can do it. Now, what if you're in the situation where you missed a final, so you only have miss one of these? Well, then you just put in whatever you get on your final is going to be one of these, will be used for one of these exam scores, so you can just estimate different amounts that you need. You can just play around with it. It's the best you can do. All right? So, any questions on that? And I will be sending, for sure, your room assignment. Make sure that where you go for the final is completely, I'll make sure it will be finalized after we deal with the conflict sign-up. After that's all finished tonight, and you'll get your location for the final. All right? It will probably be in this room, but you might have to go to a different room. Okay, so any other questions? So today all we're going to do is just go over the final exam in the notebooks. So let's just go right to that. All right. So, as I said before, this is somewhat different just because than the final you're going to see Friday, because this is not all multiple choice. But it's very similar. Okay? So let's go through this. And what I think I'll do is, we're not going to have time to go through the entire exam. So I think since we just went over the non-parametric stuff last time, since we had just covered that and that's pretty fresh in your mind, I think it's best to start with the power and go forward. And I don't think we'll get to the non-parametric stuff questions, but as you probably know, there's last semester's review over this same exam, so you can always watch that. Does that sound good? All right. So now, so let's look at these power questions. All right. So significance tests are subject to two types of errors, the type 1 and the type 2. And where do they belong in this table? So remember, when the alternative is true, you can think of that, you have a real effect. There's some real effect. Okay? So you can, so there's like a positive here. And when the null is true, null means nothing, no effect, none. So you can think of that as no effect. Okay? This might help you. And so when you reject the null, when you reject no effect, that's like rejecting no, that's like a positive, you found a positive result. And when you fail to reject the null, that means it's not that you're accepting it, but you're not finding we call that, it's like negative result. You're going along with the null, right? Okay, so now when we look at this, we can see what's questions, type 1 errors. So type 1 errors can only happen when the null is true. It's making an error when the null is true. And when the null is true, look, this is the error. You're going to reject the null. That's your error. So that's type 1. If you want to draw a little it's like you do the null cutoff under the null. This is right. That would be your type 1 error when you reject that null. All right. And the next one is the type 2 errors. Well, the type 2 errors happens when you fail to reject the null. It happens when there's a real effect and you don't detect it. So that would be right here, type 2. It's type 1 and that's type 2, right? So we have B here, belongs in B, and here is C. All right, and then, so we have an alternative. If we had an alternative, it would be up here, let's say. And then, here's your null cutoff. And when we fail to reject, right there, when we fail, we want to side with the, if there's a real effect, we want to side this way. And so this is the power of the test, and this is the type 2 error. Okay? So the power and the type 2 only happen when there's a real effect here. That's the power. Think of it as the power to detect an effect that's really there. That's all. It's powerful. You want your test to be powerful. When you really have the effect, you want it to detect it. Okay? That's all it is. And then we don't really have a name for this. This is just the boring thing right here. That nothing's going on, and that's what we pretty much found out. Okay, so now let's look at this. Is it possible to calculate the type 2 error from the type 1 error? No, it's not, because look, it depends on your alternative. Like you said, see, if we shifted our alternative around, it depends on, we'd get a different type 2 error. Even if we set this is the type 1 error, let's say we set that at 5%, well, with a different alternative, the type 2 error would change, so that's no. It depends on your particular. It depends on your particular alternative hypothesis. And also, it depends on what you choose to be the null cutoff, I guess. But that, I guess, given the null cutoff, that would give you your type 1 error. So it depends on your particular alternative. All right. So now, A large randomized experiment is done to test the effectiveness of some drug. So the researchers do a significance test, and they set the p-value to reject the null at 5%. And let's say the null hypothesis is the difference in cure rates between the drug and the placebo is 0, that there's no difference. That's the null hypothesis. The drug doesn't work. It's no better than a placebo. And the difference, in this case, in cure rates between the drug and the placebo is greater than 0. That means the drug works better. It's not just an inequality. An inequality often does happen, and that's if, let's say, you're testing a new drug and you're not sure whether it works better than the old one or better than a placebo. It could work worse. It could kill people more. So that would be not equal. But here we think it works better. Okay, so when the null is true, what's the chance the researchers will make the wrong decision and decide the drug works when it really doesn't? When the null is true, that's what that alpha is. That's what our cutoff is. That's like a type 1 error. And so if we set it at 5% here, it's 5%. So this is the same as setting our type 1 error. That's what it's doing. It's this probability that when it's really nothing's going on, you're going to mistakenly think the drug's going to work. Okay, that's the same thing. Now, how about when the null's false and the drug really does work? Okay, when the drug really does work, we want the power to detect it, right? There is a difference. It's not 0. But that we don't have enough information because, as we said right here, it depends on your particular alternative. Okay, so now let's look down here, and please stop me if you have any questions anywhere along the line. Okay, so now let's look down here, and it says, suppose the researchers do specify an alternative hypothesis. And where they specify it, let's see, this sets the cure rate for the drug at exactly the null cutoff. Exactly the null cutoff. So I didn't draw them side by side. I could have. Exactly at the null cutoff would be if I moved this over so that the middle, this 0 right here, was right here at the null cutoff. That's what it means. Oh, sorry. And if I was doing this, I would just move this right over so 0 was right at this null cutoff. So half the graph would be on this side. You know, you can imagine, here I drew the picture. Okay, down here I just drew it. So the null cutoff, which pair of histograms represents that situation? Well, here's our null cutoff. It's the same for each one of those, right? We have this 5% error here. That's where for one-sided, that's very hard to see, and I'm sorry. Okay, that's 1.65, meaning this is 5% here. Now, in each one of these, but now we have different alternatives. Now, which one do you think sets, you see how the alternative is setting the most likely value of the alternative, right here at 0, right at the null cutoff is this one, right here. Okay? That's the one that most closely represents it. This one, what did we do? We set the null cutoff, 1.65, at what? That looks like about right here, that looks like negative 1.65. And right here, that's negative 1. But right here, we set it at 0, right there. Okay, does everybody understand that? And now the question is, if you did that, if that was the case, there's still a difference. You know, we're still shifted over. We're still, certainly there's a difference between the null and the, it's not 0. But how often would we pick up that difference if this was the case? We'd only pick it up when? Here's our power. We'd only pick it up 50% of the time. And our type 2 error would be 50% of the time that the null is, when the alternative really is true, our power to detect it is going to be just 50%. Does that make sense? So what is the power of the test? It's 50%. When the alternative is true, it's 50%. Sorry, I didn't hear your question. Who's? Yeah, yeah. The null cutoff is always, his question is the null cutoff 0? The null cutoff is always decided with, given the null, for the null. It's the null cutoff, it's up here. And when our alternative, we set our alternative, so our alternative, the expected value of the alternative was set right at that null cutoff. That would be terrible. We'd only detect it when the alternative is true. If the alternative was true, and there is a difference, you can see, they're not, we'd only detect that difference 50% of the time. Does that make sense? Does that make sense to everybody else? But if we set it, so yeah, I mean, there is a difference. Look, it's the expected value here. We're either in this situation or that situation. And if we're in this situation, yeah, we're wrong 5% of the time, and we're going to reject the null when we shouldn't be. We're going to say, hey, the drug works, when it doesn't. But now, let's say we really did discover a good drug. It does work. It works. It works. But we have to, 50% of the time, we're not going to realize that by this test. How about on this test? What percent of the time would we realize? Let's just do the same thing. What's the power of this test? Well, right here, excuse me, this is the type 2 error here. And that would be what, if we set it? Wouldn't that be 5%? Right? So that would be 5%. So then our power would be 95%. Here we have 95, here we have 50. And what do we have here? Can you figure that out? Between 1 and -1 is 68%. So that means this tail has to be 16. So this would be 16%, so this would be 84% power. That would be 16%. That would be your time. You'd make a type 2 error. Here, 50% of the time you're making a type 2 error. And here, this is exactly symmetrical. You make it, your type 1 and your type 2 errors are just the same. So that's the idea there. Now, I know there's a lot to learn. This is the base. This stuff is very important, by the way, extremely important. As I said, the meaning of a p-value is something that even people who have taken a lot of statistics courses sometimes get a little confused on. So at any job interview you have, it'll be impressive if you can make sure you understand what a p-value means. So now, what else? I think, what don't you need to know? Power was, that section was difficult for a lot of people, and we came up with this really simple formula, but as I said, you don't, to calculate what sample size you need to detect a certain effect, to get a certain power, etc. And we did, I don't know if you read my email, but we're not going to have that type of question. So I showed you on exam 1 that you don't have to know, for example, how to solve for n or how to do those power calculations. Just know the ideas here. I debated that a lot to do because I really want you to know that stuff, but I know that you can always pull out your notebook, hopefully, and look at that and use it there's a lot to remember, and I just thought that was a difficult thing that people would have trouble remembering for the final. That's all. Yeah. Well, it's easier to detect a big effect, right? It's easier to detect a big effect. But do we really, so if we have a big effect, you're going to have a lot of power. But let's say, this is a smaller, if the effect in z-scores is only that big, it's going to be very hard to detect. You're not going to have much power to your test. Does that make sense? What was your question? I'm sorry, I didn't repeat your question. Your question is, why would you why would you do this? Why would you ever set your alternative right at the null cutoff? You wouldn't. I'm showing you don't do that because you'd only have 50% power. Is that your question? I'm sorry, go ahead. Can you answer her question? First of all, what was the question? Maybe you could.
No, I think the question is trying to ask, why is the cure rate at 0 for the second pass?
Why is the cure?
I know it's at.
The cure rate's not 0. The cure rate, that's it. No, the cure rate, oh, I see this mistake. Maybe if we just drew it, no, the cure rate's not at 0. It's significantly better than this one. Look, let's say we just drew it. I could draw the same curve, okay, and here's the cure rate, okay. So here, when the null is true, the cure rate's not at 0, but this is the distribution right here of the evidence we're going to see gives us, this is the null, this is the curve when the null is true. Now, anything higher than this means that the alternative drug is better, anything higher. So the alternative, when you set it, let's say we set this at 5%. So yeah, anything to the right of here, even a smidgen, means that we have a better, when the alternative is true, we've got, the alternative is better than the new drug is better than the placebo. But if it happens to be just this much better, like that, then half the time our test is not sensitive enough to detect it. So what we need to do is get a bigger sample size, do something to detect it, to make it so that these curves are narrower. Make our standard error smaller, so you have these narrower curves, so we can detect that difference. Does that help you? Is that your question? The 0 is not a 0 it means just what let's say we thought the cure rate was 80% here. Maybe we thought the cure rate was 90% here. This is just means that it's 1.65 standard errors away. It doesn't mean 0. The middle of the curve is always 0. I'm just saying if it was, just to give you, just because it's easy to see that people don't realize this sometimes. You don't understand the question? Which pair? Suppose the researchers specify an alternative that happens because of your standard errors. You don't know ahead of time. You specify some alternative, then you have to calculate your standard errors, and it happens to land right at the null cutoff. That's what happens. That's what could happen. The words. Oh, suppose the researchers specify an alternative that sets the cure rate for the drug at exactly the null cutoff. Let's say they set it so that it just 1.65 standard errors away. And that would be exactly at the null cutoff, like right there. They have to set it more than that. Does that help? Okay, I think we should move on. Sometimes, and you could ask me after class. Okay? All right. Okay. And now, whoa, that doesn't look so good. I drew so many things and look what happened. All right, so now a recent study found that students who took a test immediately after reading several passages about a scientific subject retained about 50% more information 1 week later than those who just studied the material without taking a test. The subjects were 200 college students. Half were randomly assigned to read the passages and immediately taking a test measuring how much they recalled, and half were assigned to repeatedly study the passages by outlining and writing the key ideas. I thought this was very relevant. Studies like this have made me emphasize take practice exams as real exams. You will just, all the data shows that you do much better than just reviewing the material. Just actually sit down and do them. And this is a good experiment, okay, that shows that. So 1 week later, all the students took a test measuring their ability to recall facts and draw logical conclusions. Those grading the test didn't know which subjects were in which group. Those in the test group recalled more facts and were better able to draw logical conclusions than those who repeatedly studied the material. So, which conclusion is best supported by the evidence? Choose one. Well, what do you think? This is a randomized. So that means we can conclude what? First of all, it's randomized, so we can conclude causation. It's not going to have any confounders. Causation. Okay? This looks kind of messy. I think this is better to move to this one at this point. All right? So it's randomized so we can conclude causation. And so which conclusion is best supported by the evidence? Well, the study provides strong evidence. What? That among this group that test taking was the better method because it was a randomized study. That's why I really want to do a randomized study on assigning people to the in-person or the online class so we can really answer more conclusively which method is really better. Right now there's a lot of self-selection bias. There would be. If people were not randomly assigned, there'd be self-selection bias, like in the next one. Suppose I'd like to determine, I think a lot about these teaching methods, and I said, suppose I'd like to determine whether weekly quizzes work better than weekly homework to help students learn better. But here, I decide to offer a 15-minute quiz at the end of every class and give people the option, right? So if I did this, even though everybody would love the option, it's very hard to tell what's going on because you introduce selection bias. The two groups are not the same. People who select to take the quizzes and people who don't. And that's the situation we're in with the in-person and online class. It's so much easier to conclude causation if you have a random sample. All right? So now this is the situation. What do we find out? At the end of the semester, I compared the overall averages of the two groups and find the quiz group did significantly better. But can I say it's quizzes that caused it? First of all, there were no randomized controls. There was non-historical controls. At least there was contemporary controls side by side. That's much better. That's what we're doing rather than comparing them to past semesters. But it's not ideal. There's still could be confounders. So based only on the information above, which statement is best? And that is just that there's an association. You can't conclude one way or the other, whether it caused or did not cause. So just look for that one right here. Okay, we can only conclude associated. We can't say they actually caused or didn't cause. All right, so now here is this idea is what we're trying to get at, is this idea, did the quizzes, and this is what I'm trying to get at all the time in everything I do, including this experiment that's going on now, is did the quizzes actually cause these higher exam scores? By the way, in Stat 200, so far there isn't much significant difference between the scores in the two classes, between the online and the in-person. Okay, so now, so if so, how? Or there might be a third factor. It looks like there's probably some self-selection bias, something about the people who choose the quizzes might also make them more likely to score higher on exams. And what could that be? there's some difference between, just think there's a self-selection bias going on here. There's something different maybe about the people who chose to take the quizzes that could cause them. And that would be a confounder. That would go right in here. So now you just look at these, and I think math test taking ability. The students who chose to take the quizzes instead of doing math homework, maybe they're more confident. Maybe they're better at taking math tests than those who don't, than those who choose to do the homework. So that could be a confounder. So it might not be that the quizzes are helping them. It's just a marker of students who have higher test-taking ability. That makes a lot of sense, doesn't it? That could be a confounder. And what about this option? Allowing students to study, to choose the study method that works best for them, whether it's homework or quizzes, improves the learning outcome for everyone. Well, I would love that to be true. I think it probably, in the long run, I think it very well might be true. But this experiment does not prove it, that's all. It doesn't show it at all. We can't tell from this. So it's neither, and there's no evidence for this, especially because the homework group did worse. So how can we conclude that it's better for them? That says no evidence since homework group did worse. You'd have to design a different experiment to get at that. Okay, so that's the idea there. And any questions on that? And I'll try again to make, on your final, I'll try to make a relevant example to make it easier for you, something that you know all about, to make it easier for you to do this. Oh, yeah, so I didn't do this. Oh, retrieval, thank you. Retrieval from memory, thanks a lot, rather than notes. Those who take quizzes are forced to retrieve information from their memories rather than from their notes, and that process helps cement learning. That would certainly be a causal link, and that is what people are surmising as the causal link, why test taking is better than just reviewing. That you develop these neural pathways for retrieving information that is exactly the neural pathways that you need for the real exams. So that's the theory behind why this works. The quizzes work and the test taking works. All right. Any questions? Let's move on. Okay. And let's go. All right. So let's move on to question 5 here. And in this question, you're given these 5 summary statistics. From these, you imagine these were 100 students, their homework and their final scores. And now you want to find the regression equation from this. Find the slope and intercept of the regression equation for predicting finals from homework. So predicting finals, that means finals is y, and homework is x, because we're predicting finals. All right, now what you need to know here, and this is not going to be a formula in the front, let's look and make sure, is the slope formula. Nope, it's not. These are the formulas you have right here, and the one you need is the slope, just as right for a simple regression. So what is that? Do you remember? It's r, right, times the standard deviation of the y over the standard deviation of the x. So that would be 0.3, and now it's just the ratio of, right here, these two, 20 over 10. So that gives 0.6, so that goes right in here. And then just to get the intercept, that's true for any point on the line, so it's going to be true for this point of averages. So you can just plug that in. So you can plug a 60 in for here and an 80 in for homework and see what goes here. That says 48 plus what equals 60, so that is a 12. Any questions on that? All right. Now, a 95% confidence interval for the population slope. Well, remember that a 95% confidence interval, this is our point estimate right here for the slope. So that's going to be our sample slope. And then we're putting this wiggle room around it, right? And it's going to be a 95% sure that it captures the true population slope. So it's plus or minus what? 95%, you can estimate. Look, this is multiple choice. So you could always use 2. That will give you the best. I'm not going to have one choice that's 2 and 1.9.6. And you're choosing the closest one. So just do the simplest calculation, 2. And now what are you going to put in here? You want to put, this is this slope. This is your sample slope. Right there, right? That's that. And here you want to put in what? The standard error for the slope. Now, is that given to you? I think so. It should be. Let's look. Standard error for the slope. So there you have it. Okay? So you don't have to memorize that. So we know all that. So we can just put it in. All right. So in this case, what do we have? We have the square root of 1 minus r squared. And then you have over the square root of n. N's 100. Where'd you get that from? Right up there. And then times sdy over sdx. It's that same 20 over ton. And I did that and I got 0.18. Be sure to bring a calculator. Okay. Sorry, it looks a little bad. So that's what goes right in here. Oops, it's 0.19, sorry. That's equal to 0.19, so that's what goes right here. So it's 0.6 plus or minus 0.38. So which one would that be? That one, right? Isn't it that one? Shoot, I don't have the answers written down. Yeah. Okay, I should find the answers. All right, let's do the next one. So to test the null hypothesis, all right, against this two-sided alternative, we do a z-test. Now, circle the correct z statistic. How are you going to remember that? There's probably the easiest way just to remember it is that z would be what? It would be your slope right here over your standard error for the slope. You could do it that way. So that would be what would you do then? You'd say r times the standard deviation of the, you do that, 0.6. Whoa, it's not written like that, right? So you could do r times the square root of 1 minus r squared. I think this is a hard way to do it, though. Over the square root of r times sdy over sdx. This isn't a good way to do it. You don't want to remember all this, do you? I mean, that's the slope, r times sd. I'm just wondering how the best way for you to think about this is. Let's say you're taking an exam. This would probably be last resort, right? Slope. You've already know that, r times sdy over sdx. And then you already did, this is given to you, right? Isn't this given to you? So you could just cross that out, and then you could do this, and that's going to match up with, just because it's written in terms of r up here. So that would be what? That one would be 0.3. So that's r times the square root of n over the square root of 1 minus r squared. And you can see that's what that is. It's which one? The square root of 1 minus r squared is, so that's 0.3 times 10. 0.3 times, so it's going to be 3 in the numerator, and the square root of 1 minus 0.09. So which one does that match up with? This one, right? So that would be your answer. I think there's, you know what I think is probably an easier way to do this? Are you going to all remember that z is going to be, like for this, it's going to be the square root of the chi-squared? Because this chi-squared is super easy to remember. If you know the chi-squared, it's what? R squared over 1 minus r squared times n. And then you just take the square root of that, and then you get that. That's super easy to remember. Right? And z is the square root. So you could do this, that, and then you just take the square root of that. So that then c is equal to the square root of the chi-squared. So that's where you get the r times the square root of n over the square root of 1 minus r squared. We did this a lot. I'm just trying to think of how you can put these formulas together, and because it won't be given to you from what's on the front. Any questions on that? All right. Now, the next one. If you square, oh, here it is. If you square the z, you get the chi-squared for this simple regression. And if you square the t, you get the f. So there, once you know that, and this is so easy to remember, that you're going to have to know this. This is so easy to remember. Then you just take the square root of it. Okay. Now, suppose the p-value for the hypothesis test based on the z yielded this p of 0.22%. Then the chi-square would yield what? Now, it's going to be either the same as that or double it, depending on whether it's one-sided or two-sided. So we have to look up here, and how do you know it's two-sided? Because it's not specifying which tail it's in. So it's going to be exactly equal, right? And how about the t-test would yield a p-value what? The t is fatter in the tails, so it's always going to yield one bigger, right? Because t and f has fatter tails. Does this make sense to everyone? All right, let's just keep going then. All right. Now, our next problem is, let's see. Okay, so now these two scatter plots below show the heart rate versus temperature for 65 males. Here's the males, and here's the females. All right. And now, is it possible that we can combine these two combine these two simple regression? Here you have this slope and intercept, this slope and that intercept. They're two different ones, into a multiple regression of the form of this form. By, just adding a gender variable. That's all we're doing, is adding a 0, 1 gender variable that would yield exactly the same predictions as these. Well, it would take care of look, there's no intercept term there. So when we put in a difference for the gender term, like 0 or 1, if we put in it, that's going to, if it's a 0, 1, that's going to change the intercept. It will do, whatever's coded as 1 will have this much more than what's ever coded as 0 for their intercept, because there's no other term there. So that would take care of this, but we have two different slopes here. Do you see what I'm saying? We could do it if these two were the same, but they're not. They're two different slopes, so we need an interaction term. So no. Does that make sense to everyone? Okay, now which of the following multiple regression equations yield exactly the same predictions? So you have to have one with an interaction term, so don't even think about the ones that don't, as these two. So the question is asking, which yield the same predictions for all values as the two simple regressions. And it gives you this piece of information. All right, circle all that do. Well, no interaction term, they couldn't possibly. So it's either this one or none. Now right away, the interaction term is going to be what? It's going to be the two predictor variables multiplied by each other. It's never going to be the you're never going to have heart rate in terms of heart rate. Y in terms of Y, no. So this one clearly is another one eliminated. So now the only thing you need to do is to see whether this equation would actually yield the same thing. So you could just try it when you plug a 0 in for gender, right here, and right here. Plug a 0 in for both of them. Do you get the male equation? So when you plug a 0 in for both of them, do you get this? Yes. When you plug a 1 in for gender, do you get that? Yes. You get negative 88 minus 149 is that. And if you plug a 1 in for here, you get 1.6 plus 1.5 is 3.1. Let's say you had to figure that out on your own, what to put here, what would you do? Right here, to get the 149, how would you get that? When you want for the intercept negative 237. You want that, negative 237, but you already have a negative 88, so you'd have to add 88. And that's how they got the negative 149. If this wasn't given to you, how do you get that? How do you get the 1.5? Well, you just look and see what you really want is 3.1. But you have 1.6, so you'd have to subtract it off. And that's how you get the 1.5. So that was pretty easy. We've done that a lot. So questions on that? All right. And now, this. So the A and B are two drugs, and the four numbers in the tables below indicate the mean response to neither an A nor B, A alone, B alone, and both together, fill in the blanks so the models and the data match. Well, there's no interaction here. All right, and what am I supposed to fill in? If there's no interaction, okay, no interaction means 5 plus 6 equals 11. So 7 plus 6 is going to be the same slope, will be equal to 13. Or you could say 5 plus 2 equals 7, so 11 plus 2 equals 13. That's very easy. Now let's build a model based on this. So first of all, when A and B are all 0, what goes in here? 5. Now, when B is 0, forget about these, and you just move in this direction from A equals 0 to 1, we're adding 6. So that's plus 6 equals 11. And how about here, B? Just think about, in this situation, A is 0, so that is eliminated. And so 5 plus 2 gives you the 7. Okay, so that works for everything in the table except this 20, right? If there was no interaction, we have 5 plus 6 plus 2 would be 13. That should be a 13, right? But we didn't get 13. We got 20, so we have to add an interaction term of 7. Because that equals the 20 that's here. Right? All this together gives you 13. And then when A and B are both present, like right here, you have to add 7 more. So that's an interaction term. All right, I think that's pretty simple, and let's move on. And what are we doing next? So, this is data what? Summarizing statewide violent crime rate. This was actual data I pulled off a website for each of the 50 states and Washington, D.C. Okay, so that's why we have 51 here, because we're including Washington, D.C. And so we have the average, And so these are, okay, what are we going to try to do now? Well, first of all, we want the correlation matrix describing R between the three variables, all right? So this is just reading the correlation matrix. It's pretty easy, and fill in the 4 blanks. So the violent crime and violent crime, this along the diagonal here is clearly just going to be 1s, because the correlation between X and itself, between murder rate's 1. So we know that. And then it's symmetrical, because the correlation between these two, below poverty and violent crime, is going to be the same as violent crime and below poverty, right? So this is the same. So this would just be symmetrical with that. And these are symmetrical. All right. Now, the slope, we've already done this for predicting murder rate from violent crime rate, and the simple regression is what? Well, what is, remember, it's R times SD. Which one's Y? Murder rate, predicting murder rate, over SDX. So that's violent crime. So we have to find our R between murder rate and violent crime. Right here is 0. Oh, we have choices. 0.8440. And then where's our, we have to do the ratio of the standard deviations between these two. So it's this one and that one. And we want this one on top because it's Y. So it's right here. Okay? All right. It's this one. Now, here's the multiple regression. Okay, so now we're predicting murder rate from violent crime. That would be the slope if it was in the simple regression. But now we have a multiple regression, and we're also saying, well, there's a correlation between violent crime and below poverty rate. You can see that. What is that correlation? Violent crime and below the poverty rate, they're correlated too. So now we have 3 positively correlated variables. So this is not the same as that. If we calculated this, it's 0.21, and I bet it's going to go down here. Yes, it went down. And it went down because these are partial slopes. What it does, what this slope says is that after you control for below the poverty rate, you take people at the same poverty rate, then how much does violent crime help you predict the murder rate? And it's going to be less because they're both positively correlated. Okay, so compare the slope for the violent crime in the multiple to the slope in the simple, and it went down. Why? Because you've got, okay, so you've got crime, right, and poverty, and they're positively correlated, and they're both positively correlated with the murder. So they're not independent of each other. If they were, then the slopes would be the same, but they're not. They're correlated with each other. There's a mixture of them. So once you include, you'd be almost double counting if you didn't subtract something off from them. They're separate effects. In the simple regression effects are going to be, if they're independent, that would be the same. But now you're going to be double counting here. So you have to, they're positively correlated with each other. It's right here. If they're negatively correlated with each other, they could go up. Okay. And if they're a mixture, it's complicated. But this is the easiest case to see. So now let's move on, and let's see what else we're doing here. So, all right. Now this, what did I say? To test the null hypothesis that all the slopes are equal to 0 in the population, the computer did a chi-square test and an F-test. You can see the portions of the output below. However, doing a significance test isn't appropriate here because it's difficult to translate this situation into independent random draws from a wider population. We can do that with Stat 100 because we can imagine another population, or stat 200, of similar students. Like, you know, you can imagine there's, students like you. But what does it mean to imagine a wider population of similar states? They don't exist and they're not similar to each. I mean, I wouldn't even know what that meant. So it doesn't really make sense at all to do a significance test. Yes, people do this all the time. I mean, I got this data off some place where people are doing stuff like this, but what are they really trying to do? It doesn't really make sense. So you might think, we already know the slopes aren't equal to 0. It doesn't make sense to test that null hypothesis. You can try to you can imagine if some new state came in, well, what would that state look like that you want to try to predict? All right, so will the results of the chi-squared and the f-test alert you that a significance test isn't appropriate? Will you get crazy results because it doesn't make sense to do a significance test here? Do you think yes or no? Like, will running it through this software like tell you, hey, no, you can't do this? The answer is no. There's no way to tell from the calculations itself because significance tests don't test the assumptions. The basic assumption is about there's some random element, either random assignment to treatment and control, or some way to think of it as what you're measuring is this random variation, and we don't have that. We don't have that situation. So the no, because why? Significance tests assume random draws, but they don't test them, right? Significant tests assume some kind of random draw or random assignment. But don't test them. It says, but don't test them. So you can't tell from the calculations yourself. And this is a big wake-up call to everybody. There's all those assumptions that we talk about. You can run the test, and you can get some results. But that's why we have to be very careful about checking our assumptions and checking the scatter plots, seeing what they look like, and so forth, and thinking about it, and thinking about what is our goal here? What are we really trying to get at? And what should we do? All right. So now let's see the value for, now we're just going to look at this test. So let's see. Let's see if they do. The value for the chi-square statistic is missing in the printout below. Calculated from the numbers given. All right, so do this calculation from these numbers, and here's where you should know, remember, that the chi-square is what? R squared over 1 minus R. It's a signal to noise, right? R squared over 1 minus R squared, and the chi-squared is super easy. You just multiply by n. You don't have to do that, any kind of adjustment like you do for the f. This is super easy. And when we do that, what do we get? We'd get this divided by 1 minus R squared times that. So this is what we're using as R. We just have to square it, and here's your n. Okay, and I did it, and I got 151.84. That's what that is. Now you look at that, whoa, that's a huge chi-square, right? The p-value is 0 because you'd expect to get with the chi-square, how many degrees of freedom do we have? Let's think about it. We'll fill that in here. Here's the ANOVA table for the 6 missing blanks. Show work for how you got all the answers except the degrees of freedom. All right, so you're not going to see something like this on your test, but I've been writing the test, and I'll say something like fill in certain of these blanks, like fill in 2 of the blanks or 3 of the blanks or something like that, and I'll tell you which ones to fill in. So you will have a table like that. All right? So how are we going to do this? We have to fill in all of them. Whoa. All right. So how should we begin? Do you want you want to go through this and fill it in? Let's remember how to do this. All right. So let's say I'm trying to think. Let's say, okay, so how are you going to think about this? So this is your sum of squares total, right? And this, your model and your error, so this divides it up into 2 pieces. This is going to be R squared times that, right? And this is going to be 1 minus R squared times that. And here's r squared. So we can just multiply r squared times that, and it will give us this one, right? So we can do that. We can say 0.7485. That's the proportion that's going to, of that. It's due to our model. This is our model. And that's equal to 1370. I got 0.14. Well, now you know what this one is, because they have to add up, right? So you could just say, or you could just say 1 minus r squared, but you could just say 130 minus that. 1830.51 minus that. It's probably the easiest way to do it. And you get 460.3. All right, now your degrees of freedom. How are you going to remember this? The easiest way, I think, to remember it is the total's always going to be n minus 1. That's what you're going to put in here. That's always going to be it. That's just the sum of squares total. You have no parameter. There's just a variation around y. So you have n minus p. You just have one parameter. Just one parameter. It's all just this is just your variation around all your y variables. Sum of squares total. So it's n minus 1, so in this case, it's going to be 50. And now you know this one would be 48, right? But in general, you know that this is your number of parameters minus 1. Let's say you're starting from scratch, because you probably are. So let's do this. So, so you have this murder rate you're trying to predict. So that's your y, the murder rate. And how many parameters do you have? You have your intercept, right? Plus, you're going to have a slope times the crime variable plus a slope B2 times the poverty. And that is your model. All right, so now that model has 3 parameters that you're estimating, right? So that's P is equal to 3. 3 parameters, 1, 2, 3, the intercept in those. Now, your degrees of freedom are always what? Here for the model, degrees of freedom for the model. So your degrees of freedom for the model here is always the number of your parameters minus 1. So this is P minus 1 always. And this, for your error, this is for your model degrees of freedom. And for your error degrees of freedom, it's always what? It's always n minus p. And when they add them up, you add these up, that's the p's cancel out, and that's how you always get n minus 1. So it's easy to see. All right? All right. Now, the error depends on each little point. That's why you have such a big error degree of freedom, because it depends on every little point has an error. All the n's have an error, except you've already estimated some of the parameters, so you subtract those off, right? So it's n minus p. And here, your model depends on your slopes. They're predicting it. But we've already dealt with this one here. We've already estimated. So that's why it's the number of parameters minus that intercept, because it's already dealt with here. So that's how it adds up. Okay? That's it. So you should be able to remember that. P minus 1 and n minus p add up to n minus 1. All right, now to get, that's your mean square. Now what do you do to get, you know how you got that? That's just your sum of squares divided by the degrees of freedom. And here I'm asking you to do the same thing, get the mean square for error. It's like a mean. It's just a mean of these divided by how many degrees. You're dividing by the degrees of freedom is all. So it's 460. This is wrong? Oh, wait a minute. I got to look at the, I have the answers here. Sorry about that. I must have copied them down wrong or done it wrong. So it's 460.37. Okay. Thank you. Thank you. 460.37 divided by 48. And that's 9.59. Sorry, this looks so messy. And then your F is just, it's not going to be, on the final, on the one you see, the calculations are simpler. That's one thing about a multiple choice. And the great thing about the multiple choice is, what is the answer here? Sorry. Is it 71.4? That. The great thing about the multiple choice is that if you make a careless mistake, it's probably not going to show up on your answer. So it's a great way, it won't harm you as much. Don't you think that would be helpful? All right, so that's it. And you can see that this is a tiny, tiny p-value here. And what else? Is that it? I think that's pretty much it. So we had, basically all we're doing, if you wanted to check it, was what? F is, another way to do it would be what? R squared over 1 minus R squared. And instead of multiplying by n, instead of multiplying, you have to make that little adjustment, n minus p, right, over p minus 1. All right, can you tell? No, you can't tell. You can't tell. It's not going to alert you that you did anything wrong. So any questions on that? Boy, we're running pretty slow here. I guess we have 15 minutes. We could finish more. So now, what are we doing here? All right, so now we're doing just this analysis of variance type of model here. And it says, okay, so here's a situation where you have 894 Stat 100 students, and they reported the percent of tuition their parents paid, and they also classified their hometown into the 4 types here. And imagine the students were randomly sampled from a much larger population. You can imagine that, right? And here's, I guess these add up, these should add up to 894. And compute the chi-square test to test the null that all the group means are the same in the population and show work. So this is really easy. It's just going to be r squared over 1 minus r squared times n. So that will be 0.3 squared over 1 minus 0.3 squared times 894. Okay, and I got, when I did that, 88.42. All right. That's the chi-squared. How many degrees of freedom for the chi-squared? The chi-squared degrees of freedom is the same as the numerator for the f. It's just, you don't make that pesky little difference with how many, which you're adjusting n. But so it's just the number of parameters minus 1. The number of degrees of freedom is always your number of parameters minus 1. And here, how many parameters do you have? What are you, you're estimating what? You're estimating how many parameters? 4. 4. You're estimating the average for 4 groups. You're estimating 4 parameters. We have no intercept here. We're estimating 4 parameters. So P is equal to the number of groups. Right? P and G. So it's P minus 1, G minus 1. They're the same thing. That's the number of parameters you have because you're estimating 4 parameters. We're not, if we did an intercept, which you can do that all the time, put it into a linear model. That's what you usually do when you want to get estimates of the differences between the groups. Then you have 1 intercept and 3. You choose 1 as the baseline, and then you have 3 slopes, exactly like a regression model. These 2 things are the same. This is a special case of multiple regression. So those parameters, those degrees of freedom are the same. It's just the number of parameters is the number of groups here. Okay? So what is that? 4 minus 1, which is 3. So that's your degrees of freedom. All right. Now, the p-value is less than, look at this. Look at this for the chi. It's this. The expected value would be 3. You'd expect, when the null is, if there's no difference between the groups, you'd expect 3. And we got this giant chi-square statistic. Okay, so what do you conclude? We conclude what? Just that at least one of the groups is significantly. What if we wanted to test the groups? How do we do this? Well, there's how many pairs of groups? There's 4 times 3 divided by 2. There's 6 pairwise comparisons that we're going to be making. And for each one of them, what would we do? Well, compute the t-statistic to test whether the difference between small town and big city is significant. And you have to use this. I'm giving you this, what the standard deviation plus is right here. All right, that's based on all the data. So what are we going to do? It's just going to be that times the square root of 1 over, we have to adjust for the different sample sizes for the two groups. And we're doing small town and big city. So this is small town and this is big city. So it's this one right here. That's not given to you. Now, what is the t-statistic? Well, it will just be our observed difference minus the expected difference between, so what's our observed, we're testing whether these averages are the same. So between big city, small town and big city, it's 53 minus 40, right? So it's the difference. This is your observed difference between the two cities minus your expected difference, which is 0, over your standard error for the difference. So we're talking about the difference between the two cities, which is 53 minus 40 minus 0. So that's 13. Oh, there's only, it's this one. And how many degrees of freedom? Now this is how are you going to think about this? This is based on what? The degrees of freedom are, when you do a two-sample t-test, it's just n minus 1, right? But here it's because you only have one parameter. Here it's n minus the number of parameters, which is n minus p, which is equal to n minus g, which is equal to what? 894 minus 4. So it's 890. Because it's based on all the points, all n points. They're using this standard deviation here is a pooled estimate based on the null is that there's no difference between these groups. So so it's as if they all have the same, you're just basing it on all the groups put together. So you're basing it on all 894 points, but then you have to subtract off however many you've estimated those group averages. All right, so now this is the p-value, but now because you're going to have to adjust that. You're going to have to multiply it because it's we didn't specify ahead of time. We're doing these post hoc tests, so we multiply by the number of groups, by the number of pairwise comparisons. And the number of comparisons, unordered comparisons, it's g times g minus 1. That's how many comparisons there are, but we don't care which direction. We're just, we don't, like here, we don't care which way we subtract, 53 minus 40 or 40 minus 53. We're just looking for a difference. So that's why we divide by 2. And we get 4 times 3 over 2. Okay? Remember when we did the u-stat? We looked at the number of comparisons. It was just, but we didn't have to divide by 2 because we cared which side. They were ordered comparisons. All right, let's go to the next page. There's a lot we learned here. Oh, how long does this go on? This seems never ending, right? All right, I need a drink of water. Oh, let's look at this one. Oh, look, this is great. On this exam, I don't know if I gave you a way to check. Now we'll do the same problem to test to see if there's any differences between the 4 group means in the population by filling in the 10 missing blanks in the ANOVA table below and computing the f-stat. Whoa. Okay, let's do this then. So, well, this is pretty easy. I think you know how to do this, right? Do you want me to fill this out? We've just talked about this so many times. The number of parameters is equal to 4, right? Because we have 4 groups. G is equal to 4 groups. And N is equal to what? 894. So there's where we have it. That's where we have 893 right there, right? And now what are we going to have here? The model's based on the groups. That's what we're trying to say. Are those group memberships, what group you're in? Is that going to be predictive of how much tuition your parents are paying? So that's what? G minus 1 or P minus 1, and that is 3. And here is N minus P or N minus G, same difference. They have to add up, and that's 890. This plus this equals that, so I think I don't have to write it, right? Just subtract that from this. And, oh, look, I even gave you, you can multiply that by that, and you should get that. All right, now what else do we need? These two, the ratio, that's what the F is, the ratio of that to that. So let's do that. So that's 42,000 over that. Round to 2 decimal places, and I got 29.34. Even without a chart, you know, remember this, you should know this, when the null is true, what do we have? The mean of F stat. I like this F stat, this is the whole point. It normalizes, it makes the mean 1, right? And the chi-square stat is not centered at its at 1. It's centered at its degrees of freedom. So it's going to be the chi-square stat is going to be this degrees of freedom, which is equal to P minus 1 or G minus 1 in this case. All right, so that's at 1, and this one would be, however, this would be 3 here. But look how much bigger this is than that. So yes. So now here, this is just the square root of that. And you can see right here, it's based on N. See, look, that SD plus errors right here that we're using for all the groups is based on N minus G points. That's why the t-test has not N minus 1 degrees of freedom, not N minus 2 degrees of freedom. It has N minus 2 if it's simple regression, N minus 1 if it's just means, not regression at all, just an average. But in multiple regression, it's the same thing. It's always N minus the number of parameters. And with simple regression, there's 2 parameters. That's why you have N minus 2. All right, now this, I think this is finished, isn't it? Oh, R squared. How would you get that? Yeah, exactly. It's always the ratio of this to this. So it's SSB over SST, right? And sum of squares model over sum of squares total. So you do that over that, and I got 0.09. All right, so I think that's finished. Boy, that exam 2 test had a lot of material. And now we finally get to exam 3. And I think you're more likely, I think this you know pretty well. I don't think I have to go over it. We just had exam 3. So I think you can watch this on the video. I think you just needed, and I'm very, I guess you just need to review that power and come in for office hours if you didn't understand that. I mean, sometimes this always happens with power and with type 1 and type 2 errors. You just get a block and don't worry about it. I'm sure you'll be able to figure out that, and if you don't, just come see me. It happens to everybody. You just get mixed up with the type 1 and type 2 errors. So just come see me, and I'll explain it. I can explain it right now if anybody wants to. So good luck, and see you at the final. And don't forget, if you want to sign up if you want to take it Friday night instead of Friday morning, you can do that if you're a night person.